И что-то еще надо. Ты.
Живобушка?
Да? Все, вообще.
Как лучше, чтобы у вас был видно, чтобы вы так можно сделать.
Я бы сказал, что
Okay. So we will continue today setting up some notations, but hopefully on Friday we will start constructing characters. So something interesting will happen on Friday, but not today. So let's just recall. For the introduction. So we have a partition, and not a partition, rather a composition. Equals M1 plus so on plus and so R. And we associate to this flag in our n-dimensional space. So V I is spanned by the basis vectors E1 and so on up to E M1 plus so on plus so I. Okay, so these and i's are the dimensions of the associated gradient coordinates. The flag F or maybe V. This and the P parabolic subgroup is the stabilizer in our group GLM over this flag. So in the block notation, this is the set of matrices. This R, and then something here, but 0 below, block diagonal. And now given central functions UI on the groups G and I, we can consider their product. U of G I. So it depends only on the diagonal blocks, not on the upper triangular part. And this is a central function on our subgroup. So it factors through the quotient map to the product of GLN. Yeah, it's independent of the unipotent radical. Okay, and now we set U1, UR is the parabolic induction. So from P to GLN of this function U. Now we shall write a formula for this function in terms of the structure constants of the whole algebra, as promised a long time ago. In fact, we did this for the functions unipotently supported, but now we will allow arbitrary eigenvalues. Well, let's consider the partition into the left cosets. This cosets and then we can write the formula for this induction. So U1, UR, the value of this at an element X is the sum over all left cosets, U over Zi inverse X Zi. Okay. Well, meaning that if you get out of parabolic subgroup, then it's zero. Yeah. So U is supported on the parabolic subgroup. Okay. So note that this conjugation Zi lies in P in the support of this function if and only if X preserves the shifted flag ZIF. Okay, here's our flag. Okay. Yeah, so that this shift ZIF is a flag over submodules in X. So as we argued many times, any element in GLN or any matrix at all defines a model over the ring of polynomials, where T acts as X. Okay, and now, well, since this flag is preserved by X, it means that it's the flag of the submodules in this model. Okay, so we do denote Wi is the Vi, and the inverse x z. It lies in parabolic subgroup, so it has the form h11 and so on, hrr 0 something. So then the associated graded quotient Wi modulo W I minus 1 is again model over K of t, the corresponding to the element Hi, well Hii. Okay. So, well, the conclusion is that this whole composition of functions, the value at the conjugacy class mu. Well, last time we introduced this notation, yeah. Well, the eigenvalues are numbered by irreducible polynomials over FQ with a leading term 1, well, but with the exception of polynomial t. And we associate to each such polynomial, or in other words, a Frobenius orbit in the algebraic closure of FQ, we associate a partition. This association is called mu underline. It's a collection of partitions for any irreducible polynomial. Then this is a numbering for conjugacy classes. And then namely, a partition associated to this polynomial denotes the Jordan block with such eigenvalues. So this is equal to sum of certain structure constants, mu 1, so on, mu r, and then you take u1 over partition class C mu 1 times so on times u r of the conjugacy class corresponding to partition R. Okay, now the sum runs over all collections of these multi-partitions. Such that the size of mu I is ni. So it corresponds to conjugacy class and G and I. Okay. And the structure constants G mu 1, so mu R is the number of flags 0, W1, W R. So our mu, well, it defines the type of module over polynomial ring. Well, such that the associated grade W has the type corresponding to those partitions. So it's just a stupid, straightforward repetition of what we had before. Only before everything was numbered just by partitions, everything was unipotent or nilpotent. And now everything is numbered by those multi-partitions of functions from irreducible polynomials to partitions. Okay. So let me rewrite this yet once again. So set delta mu is the characteristic function of the continuous class C mu. Okay. Then the product of those characteristic functions, delta mu 1 times delta mu r is the sum of those structure constants mu 1 mu r delta mu. Okay, and finally, those structure constants are the ones where they static. And this is the only essential statement to claim that the structure constants are the products over all irreducible polynomials. Of the structure constants that we studied. Or f. Now this is just a partition. Mu 1 of f, also a partition, and so on. Mu r of f. Okay. So the structure constants in the Euro-Hall algebra only must specify the ring that we apply it to. And the ring is associated to this polynomial f. Yeah, so there's just the localization of the polynomial ring in this maximal ideal f. Okay, so this is what we call O. Fine. So that's the only essential claim I've made so far. Now, we introduce important notation. So an is the set of central functions on GLN. So it's a vector space with a basis delta mu such that the size mu is n. And with a Hermitian scalar product. U and V is just the usual scalar product G times V bar of G. Okay, and then since we just introduced this operation of parabolic induction, it makes sense to consider the direct sum of all those spaces, and then it is an algebra with respect to the parabolic induction structure. This product. Okay, and the again another conclusion is that A is isomorphic to the whole algebra with the scalars extended to complex numbers, because we consider complex valued functions. So here H is the tensor product over many copies of the whole algebra, not numbered by those irreducible polynomials. Well, whole algebras, many, well, copies of, I don't know, of whole algebras. H of a polynomial ring localized in maximal ideal F, well, maybe tensor product over all F irreducible polynomials. Okay. Okay, and the last definition in this series is that Rn inside An is the Z submodule generated by the characters Gn. Okay. Well, then by definition, R, which is the sum of all Rn, is a subring in the whole of A. And also, A is just the extension of scalars from integers to complex numbers. Okay. And somehow, as I mentioned a few times, we are just mimicking the Frobenius approach to computation of characters of symmetric groups, and this is, so to say, the only point of departure, because well, maybe a posteriori, but it's the fact that all the characters of symmetric groups are integer valued. Okay, so we never need complex numbers at all. It's a priori it's not evident, and well, you prove it at some point, but in reality you don't need complex numbers at all. Everything works over integers. But here certainly it's not so. Yeah, but you already know about the characters of GL2, even about GL1. Yeah, you just consider characters of the polynomial group of finite field. Certainly they take some complex values. So they are not integer valued. Okay, and this is an important point, because the argument, as I said, will be sort of ad hoc. We will produce certain candidates to characters, and then we will see that they
generate the same Z module as R, and they form an orthonormal base of this module, and so they must be plus minus characters. Okay, this will be the argument the same as in Frobenius case, but somehow we will need some integral structure. So it will be important to identify this Z subring inside of this complex valued ring. Okay.
And this part this difficulty is missing for symmetric groups. So this is the only new
Feature.
Okay. And now again we repeat the Frobenius approach. So we construct a characteristic map from our algebra A or
Then R to the algebra of symmetric functions. Yeah, the one that for symmetric groups, for the case of Frobenius, it takes, let's say, the delta, or the characteristic functions of conjugacy classes to power sum functions. Yeah, but then we prove that it takes the characters to Schur functions, and that's the whole thing. Now we will repeat this
in our situation. And again, somehow you just consider many copies numbered by irreducible polynomials or of the same thing that takes conjugacy classes to whole group of polynomials. And then we will, so this defines our map. Then in this symmetric function part, multiplied by irreducible polynomials, you introduce Schur functions, again numbered by irreducible polynomials, and they will be our characters. So this requires some proof, but that's the answer. Okay. So for any irreducible polynomial, we consider the corresponding variables. Oops. X1 f, x2 f, and so on. So usually our symmetric functions are symmetric functions in variables x1, x2, and so on. And now we have many groups of variables numbered by irreducible polynomials. One group for each polynomial. For a symmetric function. U. We set U of f is U in this group of variables. Okay. Now we define another important guy, B. This is the polynomial algebra. Well, polynomial algebra in variables En, elementary symmetric functions of f, oh, sorry. So over all degrees n, over all polynomials, series of polynomials. Now what we also say, degree of variable x I f is equal to the degree of polynomial f, and hence the degree of this En of f is n times degree of f. Okay, what else do we consider? We consider the Hollywood polynomials, p lambda of f, a little bit renormalized, is qf to the power negative n of lambda, p lambda of the f group of variables, qf inverse, and well, recall that qf is q to the power degree of f. So it's the well, the cardinality of the residue field of this discrete foliation ring. Okay. What else do we consider? We also consider Q polynomials, a little bit renormalized. This is QF to the power size of lambda plus n of lambda, Q lambda of f group of variables, and QF inverse. So given colored partition mu from F to partitions, we set P tilde with index this colored partition, not just one partition, multi-partition, is the product over all irreducible polynomials of these guys, each in its own group of variables. The same for Q. Q tilde multi-partition. Okay, and then this is equal to, this is a renormalization of the P Hollywood polynomial. There's A mu times P tilde mu, and A mu is the number of elements in the centralizer in GL, and well, over the class X, this class C mu. Okay, and well, the degree of this multi-symmetric function
P is the same as the degree for Q and is equal to the total size of mu. Okay, now we introduce the Hermitian scalar product. On B, just by the requirement that P and Q form the dual bases. Okay, and finally the characteristic map. Character from A to B is defined as a character of the characteristic function of the conjugacy class mu is the renormalized whole little polynomial. Okay. Oops, sorry. What shall I do? Sorry.
Наверху,
Which?
в правом верхнем углу, там квадратик рядом с...
Here?
Да,
No?
да.
Thanks. Good. Thank you. So now, for a change proposition, that this characteristic map is an isometric algebra isomorphism from A to B. There's essentially nothing to prove. I mean, we already did all the job before. So it is an algebra homomorphism. Since the structure constants match, and an isometry just because of this, because those renormalization constants for Q in terms of P are the Cornelius of centralizers. Okay, so now we have to introduce the would-be characters. Sure. Functions. So recall the orthogonality relations. Sum over all lambda, q to the power size of lambda, p lambda, x, q inverse, q lambda of x and q inverse is the product over ij, 1 minus xi y j over 1 minus q xi y j. Okay, and now let's replace xi with some new variable colored in the irreducible polynomial f, and yj by some new variable colored in polynomial f as well. Okay, q to the corresponding qf, so the cardinality of the residual field, and get the equality p tilde lambda of f tensor q tilde lambda of f equals product over ij 1 minus xif tensor xjf over 1 minus qf xif tensor xjf. Okay, and now let's take product over all irreducible polynomials. What do we get? Here, right? We get the sum over all multi-partitions, p new color, q tilde new color is the product over all irreducible polynomials, product over and j, 1 minus x f tensor x g f over 1 minus u f x f tensor x g f. Now take logarithm. What do we get? Logarithm of this sum equals the sum over all irreducible polynomials, the sum over I and j, logarithm of 1 minus xif tensor xjf minus logarithm
and this is the sum over positive integers, 1 over n, the sum over inducible polynomials, the sum over powers of integers, q f to n minus 1, x I f to the power n, tensor x j f to the power n. So we're almost done. This is the sum over all positive integers, q f to the power n minus 1 times power sum pn of f tensor pn of f. Okay, this is what we wanted. Well, now we define for x in M. M, you remember, was the multiplicative group of the algebraic closure of our finite field. It was the union of Mn that were multiplicative groups of degree n extensions. So we take some element with a minimal polynomial f. Okay, and we set p tilde n of x is p n over d of f if n is divisible by d. Well, this d is the degree of f. And 0 otherwise, if it's not divisible. Yes.
1 over n go.
Did it go? No, it was my mistake, sorry. So it's the sum over n, 1 over n, and here is the sum over all f. Yeah, sorry, this it's all there. Okay. So then this function lies in Bn, okay, in our symmetric functions, and its value at x is 0 for x out of the multiplicative group of our degree n extension. So this last equality, well, we just proved. Is the logarithm
of the sum over all multi-partitions, P tilde mu tensor Q tilde mu is equal to the sum over n Q to the power n minus 1 over n, the sum over all elements in the multiplicative group, P tilde n of x, tensor P tilde n of x. Okay, and now let's recall that there was this L that was the union of two dual groups of characters. Union of Ln, and Ln was a dual group to Mn of characters. So we discussed this last time, last Friday. But the definition is not this, but that for a character xi, we set P n tilde of xi is minus 1 to the power n minus 1, the sum over all elements in the multiplicative group, the pairing of psi and x, well, the pairing with respect to this pairing of ln and mn, p n tilde of x. If psi lies in ln and 0 otherwise. So it's just a sort of Fourier transform. Over this group, but since it's a multiplicative group, it's sometimes called Mellin transform. I mean, Fourier transform is usually understood over additive group, and this is over multiplicative group, so it's rather Mellin transform. There is a notion of Fourier transform for arbitrary abelian groups, but if it's applied to multiplicative groups, it's sometimes called Mellin transform. Okay. So well, note that those guys sometimes give the same well answer. Well, I mean, we could define our symmetric functions. We defined them for irreducible polynomials, but we could define them for just elements of M. Because each element of M defines the corresponding irreducible polynomial, just its minimal polynomial. Okay, but then those functions will depend not just on an element of M, but on its Frobenius orbit. Yeah, any two conjugate elements have the same minimal polynomial and give rise to the same symmetric functions. And the same thing happens here. We defined it for elements of xi, but if you replace xi by it's Frobenius by Frobenius of Xi or Frobenius square or anything in this Frobenius orbit, it will give rise to the same function.
So P tilde M of Xi equals P tilde M of beta if beta equals Frobenius of Xi. Well, if you wish, so it's, if we tilde M of X equals P tilde M of Y, if Y equals Frobenius of X, so that P tilde N of Xi only depends on the Frobenius orbit of Xi, and well, so the orbit of elements in M, yeah, the elements in the multiplicative group of the algebraic closure of our finite field, they were the minimal polynomials, and M modulo Frobenius was phi. Okay, and now, so these govern the conjugacy classes in together with partitions, this numbered the conjugacy classes in GLM. So in a sense, this was the basic thing governing the conjugacy classes in GLM. And dually, now I'm going to consider the Frobenius orbits in L, and they will govern the characters. So L, modulo Frobenius, will be denoted capital theta. So just the set of Frobenius orbits in L. And again, some notations. Bookkeeping, so for phi, in the exercise I denoted this way, this phi, but I'm not sure I can always write it this way on the blackboard. So sometimes maybe I will write this. So for phi in capital theta, we set degree of phi is the number of elements in this orbit. Just the same as with the polynomials. Yeah, the degree of polynomial is the cardinality of the orbit of any of its roots under Frobenius. And then finally we set for any positive integer R, PR phi is P tilde RD of Xi, where Xi lies in this orbit, and D is the degree of this orbit. Okay.
So we will consider those P R phi as the power sums in the variables y, I, phi, such that the degree of any variable is the degree of phi. So finally we are done. So we can define the Schur functions as lambda of phi are defined as just the standard transition matrix from power sums to Schur functions applied to those power sums. M S P applied to P mu of phi. Okay, and given colored partition lambda from this set of Frobenius orbits in characters, partitions, we set the total size of lambda is the sum over all orbits, degree of an orbit times the size of corresponding partition. And finally, the big Schur function is the product over all Frobenius orbits and characters of the small Schur functions of the corresponding orbit. Okay, and these will be the characters. Now we will prove in a couple of weeks that they are the desired characters. And well, maybe let's continue with this long definition. So we had this script R, or calligraphic R, and it will correspond to the script S, or calligraphic S. So it's the Z submodule of the complex valued symmetric functions generated by our Schur functions. And this is a subring. So we can express
tilde over xi, just by the inverse Fourier transform or Millet transform. So we get that p and tilde of x is -1 to the power n-1 q to the power n-1 inverse. It's just the order of the multiplicative group, so it enters the inverse derivative Fourier transform. The sum over xi n, the characters of multiplicative group of degree of extension. The scalar product of xi x minus n, but now conjugate, p tilde n of xi. Okay, so this is the inverse. Mainly transform. Or in other words, the orthogonality of characters over n. Okay. And it implies that our Schur functions form a basis in this complex valued symmetric ring B. So in other words, if we take this script Z module and extend scalars from integers to complex numbers, we get our symmetric functions ring B.
I'm sorry,
Yes.
again, why is lambda form a basis?
Just because well, the power sums related to those do form a base, but you can express them in terms of those.
Okay, yes.
Okay, so now the last claim for today is that those Schur multifunctions form an orthonormal basis sorry. S. Well, consider any element in B and write it in the basis of whole Littlewood polynomials, multi-whole Littlewood polynomials. And we define complex conjugation in these terms. Just with take complex conjugates of the coefficients. Okay. Now, the logarithm of the sum of lambda s lambda of x s lambda of y is the sum over ij logarithm of 1 minus xi yj inverse, and it's the sum over n, 1 over n, Pn of x, Pn of y. So the classical Schur functions form an orthonormal base of the classical lambda ring, and it implies that the logarithm of those, the sum over all colored partitions, colored Schur functions, is the sum of 1 over n, the sum over all orbits and characters, Pn of phi, tensor Pn of phi conjugate equals the sum of 1 over n, the sum over all characters, Pn tilde of psi, tensor Pn tilde of psi conjugate. Okay, and now from definition of Pn tilde psi, this letter sum over all characters, Pn tilde of psi, tensor Pn tilde of psi conjugate is equal to the sum over all the characters, the sum over x and y in the multiplicative group of degree and extension, a pairing psi with x, the pairing of psi with y, conjugate Pn tilde of x, tensor Pn tilde of y, and finally this is q n minus 1, the sum over all elements in the multiplicative group, Pn tilde of x, tensor Pn tilde of x, well, by the orthogonality of characters of Mn. Okay. No, sorry. Something's wrong.
Что-то с ума сошел.
Okay, so maybe I just wanted to show the claim, but the claim was that they form a normal base. So we're almost done. So, well, we had an orthogonality relation that yeah, the logarithm of the sum over all multi-partitions p tilde mu and then q tilde mu was equal to the sum over n q n minus 1 over n the sum over x in the modular group Pn of x times Pn of x. So from this and that we get that the sum over s lambda times s lambda conjugate is the sum over mu p tilde mu tensor to q tilde mu. Okay, so let s lambda have coefficients r lambda mu in terms of Hollywood polynomials p tilde mu. So that it is also equal to some other expression in terms of modified Hollywood polynomials q lambda, sorry q. Okay. So from this equality we get the sum over lambda r lambda mu q conjugate lambda mu is delta mu nu. And this implies that the sum over mu r kappa mu q conjugate lambda mu is delta kappa lambda. Well, and this implies that the scalar product of s kappa, oh, sorry, and s lambda is delta kappa lambda as desired. Okay. So, well, all the preparations are done now. Congratulations. And on Friday we will start constructing the characters, and hopefully in a couple of weeks we'll be done. But did you decide about your preferences? What next?
I prefer the Sternberg representation for the minor topic.
Standard representation of the minor topic. Okay. Any other ideas? Okay. Thank you. So we go in. Stop.